Okay, welcome to Let's Calculate Something. Today we have a practical problem. It's kind of an interesting problem because it seems like you could solve it with substitution, but you really can't. It's a physics problem, and really it's about taking a rock and throwing it down a cliff and trying to figure out how high the cliff is by timing how long it takes you to hear the sound of the rock hitting the cliff, hitting the bottom. So it's kind of a tricky problem actually because you don't know, you don't know H, all you know is the total time that it took for you to drop the rock and then hear the sound. And you do know the velocity of sound at sea level, we'll talk about that. And we know that we're starting with an H, where reference is going to be up here. That's the height we're starting at. We're going to call that 0. And we know that we're not throwing the rock down, we're just dropping it from initial velocity of 0. So with all these variables, how can we actually calculate the height? It's pretty interesting because the sound is going to travel at a different speed than the acceleration of the rock, right? So the formula that we use in physics for figuring out the height, ignoring the sound part for now, is 1/2 times the acceleration of gravity times the time it takes for the rock to hit, times the initial velocity times the time that it takes for the rock to hit, plus the initial height. So we're going to call the initial height reference as 0. So that's the formula figuring out this H. We also know that the H is going to be equal to the time it takes for the sound to emanate from the rock hitting the ground back up to our ear. So that's the velocity of sound times the time. And then we know that the total time equals the time that it took to drop and the time it took for the sound to come back to us to our ear. So using these three equations, we're going to figure this out. We're going to do it in a little bit of an unconventional way. But first, let's plug in some things we do know. We do know 1/2 g, which is equals 16.1 feet per second squared. Gravity is things fall, accelerate. The acceleration of gravity is 32.2 feet per second squared, so half of that is 16.1. We know the velocity of sound at sea level is 1,117.56 feet per second. So we know that. We're going to call the reference point up here h0 equals 0 and v0 equals 0. And the time we observed, so if we had a stopwatch and dropped the rock, and then when we heard the sounds hit the stopwatch, we're going to just call it 8 seconds for this problem. So we can do some simplification. So we know what this is. We have that, so that's known. This is known. We know that. And well, we think we know it. We have this 8 seconds. That's the total, but we're going to work on that. Velocity 0 is 0. Initial velocity is 0. And the initial height is 0. Okay. So both of these will zero out for us. And basically now we can use these equations to do what we call an iterative solution. So an iterative solution is very common in engineering. And as you get to solving problems where you don't have enough equations and unknowns to match up to be able to solve a problem conventionally, you have to do it iteratively. And that involves kind of guessing at a first approximation and then recalculating something and then re-guessing based on the new calculation and constantly zeroing in on the converged solution is what we say. So let's start by trying to figure out this height here and with the information that we have. So we have h equals 16.1 times td, which we said we're going to just assume that the velocity of sound was instant and that tt equals td at first, for the first go around. And so that is going to be times 8 squared. Okay, everything else zeroed out. And that's going to equal out to be, let's see, 1030.4. So we've got our first round of an answer, for the initial height, but that's ignoring the time for sound. So now we're going to get into our iterative calculations, but before we do, this is a good time to remind you to subscribe to my channel, please. Click the bell for more notifications when I put up videos. I'm going to put up a host of videos with many topics around math and science. So hopefully you'll join and you'll subscribe and hit the notification bell. If you can, like this video if you get some value from it, and then put something in the comments. Give me some feedback. Propose some other problems you'd like to see me try to solve. That would be interesting to get some two-way communication. So, all right, let's get into the iterative part. So now that we have this initial height, assuming velocity of sound is 0 because we had the time total equal to time down, now let's figure out how long it would take for sound to travel this far. Since we know the velocity of sound, we can calculate the time for the sound, and that'll give us the first initial point of where we could start our iteration. So time sound will equal the velocity of sound divided by height. The velocity, I'm sorry, the height divided by the velocity of sound. The height is 10,030.4, and we're going to divide that by 1117.56. And I'm not going to put the units. This is feet per second. Flip it over, you get second. We're going to get, I'm not going to worry about tracing the units all the way through, just because of space. 0.922 seconds will be that initial time that we have for sound. So now, if we want to figure out the new time down, that's going to equal the time total minus the time of sound, and that's going to equal 8 minus 0.92, equal 7.08. Now, if we take this new time for the time down and put that back into our equation for height, for the height from the acceleration of gravity, we will get the new height, and I'll put a little new, equals 16.1 times 7.08 squared. All right, that's going to give us a new height of 806.58. That's pretty interesting, because when we take into the account the 0.922 initial calculation for sound, we get 8.06, very different from 1030. That's about a 20% difference, which is pretty significant. So now, because we have the new height, let's get the new time for sound to travel that height. Using this same calculation over here, we'll get 806.58. Sorry, that's very sloppy. 806 point, sorry, let's fix that. Sorry, 0.58 divided by 1117.56, and that's going to give us a new time for the sound of 0.723. So that's 0.723. So that's another correction on this original 0.922. You can see we're kind of zeroing in, taking this factor now and calculating another new h. So we got a new h here. This is going to be 16.1 times 8 minus this 0.723, which is 7.278 squared, is going to give us a new height of 852.89. Okay, so now at this point we're going to calculate a new time for sound based on this 852.89. So you can see we went from 1030 to 806, back up to 852, and we're gonna go high and low, and we're gonna zero in on that time. So I did the calculation about 6 times, and you can see from the graphic that's up there, you know, how the iteration zeroed in to the point where we got to 844. We have this height is equal to 844. Make that a little clearer. This height is equal to 844.87 feet. Okay? And the time to drop was equal to 7.244. And then the time for sound, the time for the sound to come was 0.756 seconds. So using iteration, we were able to get all the variables we needed, and we threw the rock, took 7.244 seconds for it to hit, took another 0.756 seconds for the sound to reach our ear, and both of them traveled 844.87 feet. So that's the answer, and that's an iterative solution. I'll put the more information in the links below. And again, appreciate your time to listen to this video. Pretty interesting way to solve the problem. And if there's any questions or comments, please add them. Please like and subscribe, and we'll see you next time. Thank you.